Okay, so this is our first video looking at the problem of calculating area and defining the definite integral for Math 1560, Calculus 1 at U of L for fall 2017. And here we're looking at sections 5.2 and 5.3 in the textbook. So the problem here that we're looking at, what we're interested in, is somebody gives us the graph of a function, and for now, just to keep things simple, we'll assume that this is a graph where the y values are bigger than 0. And so we've got this graph and we've got some bounds on the x values. So x goes from, say, a to b, and then there's this area that is defined as the area that's captured between the graph and the x-axis for x between a and b. And for most functions, we really don't have a good handle on how to calculate this area, right? We can do it if, well, okay, let's say if y is a constant function, right? Because then, well, then our area is just a rectangle, and we know how to find the area of a rectangle, right? Our area is going to be the base, and the base is going to be the width, which is b minus a, times the height, which is c, right? We could do it if we were dealing with, let's say, a linear function, something like this, right? Y equals mx plus b, because then, well, we can divide the area up into a rectangle and a triangle, and we know how to find both of those areas. Or in fact, you could treat this as a trapezoid. There's a formula for calculating the area of a trapezoid if you want to do it that way. We could even do it if we were dealing with something like a circle or a semicircle, right? A squared minus x squared. From minus a to a. That's something that we can figure out. In fact, the problem of calculating areas of circles is something that goes back at least to ancient Greece, and probably, I'm sure, if we looked, we could find examples in Chinese or Indian or other writings that usually don't make it into the textbooks. And so the formulas that you encounter for the circumference of a circle, area of a circle, these go at least back to Euclid. The one thing that was maybe not well known at the time is how do we actually calculate a value for pi, right? Because we know that the area should be pi r squared. Okay, so how did we calculate pi? Well, one of the first people to attempt this was Archimedes, and Archimedes had this idea that, well, we should calculate this area in terms of areas that we know. And so what he said is, let's inscribe a polygon, like a hexagon or an octagon, inside the circle. And we know how to calculate the area of a polygon, right? The Greeks knew how to do this. They knew how to calculate area for any sort of polygon, and you could work it out so that area was given in terms of r. Then you would have a slight underestimate for the area of this circle, so I suppose that would give you a slight overestimate for the value of pi, but it would give you some rough idea. And if you wanted to account for the fact that this might be an overestimate, well, I suppose you could also draw your polygon on the outside. Then the area that you calculate is going to be too big, so maybe your value for pi is too small, right? But somewhere in between the two lies the true area. And the idea that Archimedes had is, well, you can keep going with this process. He used what was called the method of exhaustion. If the estimate you get using a hexagon isn't good enough, you move to an octagon, right? If 8 sides isn't good enough, you move to 10 sides, 20 sides, you go to 50, 60, however many sides that you need. And employing this approach, he was able to get better and better estimates for the value of pi. And we are going to use a similar trick here, right? We have an area that we want, and the idea is to take that area and express it in terms of something that we know. And the something that we know is we know how to calculate areas of rectangles. And so what we do is we kind of have an initial point, so this is, we'll call this one x naught, and we have a final point b. And we put a few more points in. Okay, so we put in an x1, and x2, 3, 4, and so I guess that makes b x5. And then between each of these pairs of points, you choose a point. Say, let's just kind of mark some points here, 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 and then you take those points, you plug them into your function, and you use those values to determine the heights for some rectangles. Okay. So now what we do is we go in and we say, okay, we'll draw the first rectangle here with that height. Second rectangle is here, right, going up to there. The third rectangle is here. Fourth rectangle, we go here. The fifth rectangle is here, right? And so then we get areas. We get an area 1, 2, 3, 4, 5. Those areas are easy to calculate, and then we know that the true area is approximately the sum of the areas of the 5 rectangles that we just found, right? And the estimate that you get, it's going to depend on how you choose those points that we use to measure the heights of the rectangles, and it's going to depend on how many rectangles that you have. But one of the things that you can show is that the more rectangles you use, the better your approximation gets. And one of the ways to see this is if we just play around with a bit of software. So here's a graph. In this case, it's 1 plus square root x minus 1, and we're doing this between a equals 1 and b is equal to 9, and we try to calculate the area under the curve. So what you can see here, we're calculating area using right now just one rectangle, and there are two, so I've done two extremes here. One extreme is I chose, among any of the points I could have chose to determine the height of the rectangle, I could have chosen the left endpoint, which gives me an area which is obviously much too small. I could choose the right endpoint, which gives me an area that's obviously much too big. But what we'll see is that as you start increasing the number of rectangles, this choice doesn't matter quite so much, right? So as we keep increasing the number of rectangles, right, you see that the area we get using the left endpoint gets a lot closer to the area that we get using the right endpoint, and the true area again lies somewhere in between, just like this trick of Archimedes, right? And you keep going, and as you increase the number of rectangles, you reach a point where we can go up to say 50 rectangles. Okay. So here we see that, okay, our underestimate 22.85, our overestimate 23.3, so we can reasonably guess that the true area is somewhere around 23, give or take, right? And we can, if we wanted to improve this estimate, we could just continue to use more and more and more rectangles, okay? But occasionally approximation is all you need. So here's another example. Let's say we want to estimate the area under a specific function, okay, between, so minus 1 and plus 2. And so this time the graph looks something like this. We go up 1, 2, 3, 4. Comes down like that and like that. And so the area that we want is this area here. Okay. And so the way we do this is, again, we're going to divide things up. We might as well use 6 rectangles of equal length. So we've got these points here. So we're going to take, for our points, we're going to take x0 is minus 1, x1 is going to be minus 0.5, x2 is going to be 0, x3 is going to be 0.5, x4 is going to be 1, x5 is going to be 1.5, and then finally we end at 2. Okay, so that gives me these rectangles. Well, I need heights. How do we want to calculate heights? Let's use the left endpoints to calculate our heights. Okay, so then we get rectangles that look like this. so there we go. Oops, I didn't use left endpoint there, did I? Left endpoint should be here. There we go. And there. Okay. All right. So we'll do that. We'll use left endpoints to calculate the area. So then we would have to calculate. I don't know what happened there. Well, let's get rid of that. I don't know how to make that go away. All right, let's not worry about it. So then I calculate f of x naught. So I get f of -1 is 3. I calculate f of x1, and so I get, what do I get? 3.75. F at x2 is going to be 4. F at x3 is going to be 3.75. F of x4 is going to be 3. F at x5 is going to be, what is that? 1.75. F at x6 is going to be 0, right? And then, so those give me the heights of my rectangles, and then I would multiply each of them by the width of the rectangle. The width of each rectangle is 0.5. So I add all those up, and that's going to give me the approximation for the area. And just to save ourselves some calculator work, let's see what the computer does with that. So we're going to go 4 minus x squared. We're going to go from, it won't let me do -1. Well, let me shift things over a bit. If we do shift it 1 unit to the right, so x -1. Okay, and instead of going from -1 to 2, we'll go from 0 to 3, and that should give us the same sort of picture. And we want 6 rectangles. And so there we can see, using left endpoints, we get an approximation for the area of 7.63. We can see it right there. Using right endpoints, we would get roughly 10 for the area, and the true area is going to be somewhere in between the two, right? So somewhere around 9 is going to be our true area in this case. Okay, so in the next few videos we'll introduce some of the technical tools we need to make these ideas precise and eventually get to the definition of the definite integral.